The year 1934 witnessed the publication of a paper that, while seemingly modest in scope at the time, would leave an indelible mark on the landscape of mathematical thought. That paper, penned by Stanislaw Ulam, focused on some properties of measure-preserving transformations. To fully appreciate the significance of this work, one must first understand the intellectual terrain Ulam navigated and the enduring legacy he helped to forge. The problem of understanding measure-preserving transformations arose from a confluence of factors. The early 20th century saw intense development in both measure theory, spearheaded by figures like Henry Lebesgue and Felix Hausdorff, and in the burgeoning field of dynamical systems. Measure theory provided a rigorous foundation for the concept of size or extent, generalizing the notions of length, area, and volume. Dynamical systems, on the other hand, sought to describe the evolution of systems over time, whether they be celestial bodies, oscillating pendulums, or more abstract mathematical objects. The central question that Ulam addressed concerned the behavior of transformations that preserved the measure of sets, essentially those transformations that did not distort the size of things as they evolved. Prior to Ulam's contribution, mathematicians possessed a general grasp regarding the behavior of these transformations. They knew certain simple transformations, such as rotations or translations on a circle, preserved measure. However, a systematic, comprehensive theory was lacking. The key lay in understanding how these transformations mixed or failed to mix the space on which they acted. A transformation that mixed the space, one might imagine, behaved somewhat randomly, thoroughly dispersing elements over time. A transformation that did not mix, on the other hand, might exhibit more regular, predictable behavior. The challenge involved formalizing these intuitive notions and developing tools to analyze transformations. Ulam's 1934 paper undertook this challenge. The core of his work involved introducing and rigorously analyzing new concepts and providing novel tools for the study of measure-preserving transformations. He examined the ergodic properties of these transformations, a crucial aspect that describes their long-term behavior. In particular, Ulam focused on the notion of ergodicity, which characterizes transformations that, where applied repeatedly, eventually spread a sufficiently uniform distribution of the space. A measure-preserving transformation is ergodic if, roughly speaking, the average behavior over time is the same everywhere. Ulam provided concrete examples to illustrate the concept. For instance, he analyzed the behavior of rotations on a circle, demonstrating that rotations by irrational angles are ergodic while rational rotations are. This distinction illuminated the essential dependence of long-term behavior on the properties of the transformation itself. As mathematical definition of ergodicity was central to this The analytical tools Ulam employed involved both established techniques and innovative approaches. He relied heavily on the theory of trigonometric series, drawing on the rich mathematical arsenal developed by earlier mathematicians like Joseph Fourier. He also introduced an operator approach, leveraging the power of functional analysis to study the dynamics of transformations. Using this framework, Ulam proved several key results about the behavior of measure-preserving transformations. These results provided criteria for ergodicity and identified various classes of transformations with predictable dynamics. Critically, Ulam's work connected the abstract concept of measure preservation to concrete properties of the transformations, such as the periodicity of their orbits or the nature of their Fourier spectrum. The immediate impact of Ulam's work was felt within the relatively small community of mathematicians interested in dynamical systems and functional analysis. His paper provided a framework for understanding the long-term behavior of measure-preserving transformations, leading to the development of more sophisticated techniques. His results and insights encouraged further investigations. For example, his methods were used to analyze the behavior of systems in statistical mechanics, where concepts like ergodicity play a pivotal role. Ulam's work also contributed to a broader shift in the perception of dynamical systems. It went beyond simple geometric objects and opened the door to a more abstract, general theory, wherein the emphasis shifted towards the properties of the transformations themselves. This abstract perspective proved valuable in various applications, extending far beyond the initial context. The influence of Ulam's 1934 paper extends well beyond its immediate impact. His work helped to lay the groundwork for the development of the modern theory of dynamical systems, a theory that has found applications in a wide array of fields. One area where Ulam's contributions proved particularly significant was the study of chaos theory. Chaos theory concerns the seemingly random behavior of deterministic systems. Even though these systems' evolution is governed by precise rules, their sensitivity to initial conditions can lead to wildly unpredictable outcomes. Ulam's work offered fundamental insights into the ergodic properties of dynamical systems, the very properties that underlie chaotic behavior. Later researchers, including prominent figures like Eberhard Hopf and Paul Halmos, built upon Ulam's foundations. They refined his techniques, generalized his results, and brought further clarity to the theory of measure-preserving transformations. The development of the theory of C-star algebras, for example, incorporated many ideas developed in Ulam's work. This includes the development of spectral theory, a crucial aspect of the study of linear operators. Ulam's work was also directly utilized in a study of quantum mechanics. The study of the behavior of atoms and subatomic particles also involves measure-preserving transformations. Ulam's work served as a foundation for analyzing the quantum system's long-term behavior. The insights developed by Ulam concerning ergodicity, mixing, and other essential properties provided crucial tools for understanding quantum systems. The legacy of Ulam's 1934 paper is inextricably linked to his broader intellectual profile. Stanislaw Ulam, a polymath of the highest order, made significant contributions to mathematics, physics, and even computer science. His collaboration with Enrico Fermi on the Monte Carlo method, for example, represents one of the first applications of computational methods in science. This method relies on simulating random processes to solve complex problems. Ulam's contributions to this method, along with his work on measure-preserving transformations, demonstrates his ability to connect abstract mathematical concepts with practical problems. He possessed a unique talent for fostering collaboration and inspiring other scientists. The influence of Ulam extended not just through his publications, but through his personal interactions and his ability to see connections between seemingly unrelated fields. The reception of Ulam's 1934 paper, like many groundbreaking works, was a mixture of appreciation and a degree of initial difficulty. This arises when one challenges existing assumptions and introduces new paradigms. The conceptual framework Ulam introduced, particularly the focus on ergodic properties and the operator-theoretic methods, required a shift in perspective for some mathematicians. However, the theoretical power and the potential applications of the work became increasingly apparent. The paper's clarity of exposition and its numerous examples helped to disseminate its ideas. The paper's influence can be seen in the work of subsequent generations of mathematicians. Ulam's 1934 paper also had a crucial impact on the field of ergodic theory. Ergodic theory, which studies the long-term behavior of dynamical systems, relies heavily on the concept of measure preservation. The work provided a solid foundation for the subject and helped to establish it as a rigorous mathematical discipline. The concepts of ergodicity, mixing, and other related topics became essential tools for characterizing and understanding these systems. The work of Ulam was also heavily influenced by earlier work from mathematicians. He built heavily on the work of Henry Lebesgue, whose work on measure theory provided the foundation for Ulam's work. The ideas of Fourier analysis, which Ulam also employed, also influenced his work. The work of John von Neumann on operator algebras and functional analysis also influenced Ulam's. Similarly, Ulam's work has influenced other mathematicians and scientists. His work directly provided the tools that others used to study chaotic systems. His focus on ergodic properties provided the basic tools for these complex systems. His work also greatly influenced the work of later researchers in fluid dynamics and statistical mechanics. In conclusion, Stanislaw Ulam's 1934 paper on some properties of measure-preserving transformations represents a pivotal moment in the history of mathematics. It presented a novel perspective, a sophisticated set of tools, and a series of innovative insights. The work illuminated the ergodic properties of measure-preserving transformations, providing a rigorous foundation for the study of dynamical systems and paving the way for the development of chaos theory. His contribution, though originating in the early 1980s, has left an enduring impact. His work continues to inspire new research, demonstrating the power of mathematical abstraction and its profound influence on the world around us. The enduring legacy of Ulam's work stands as a testament to the power of mathematical insight and its ability to illuminate the complex patterns that underlie the universe.